In the previous lecture, we talked about the orbital momentum in a general way and also in application to electrons. But the same mathematics, as I mentioned, can be applied also to rotational motion of molecules. In all cases, we apply our postulates and solve equations of quantum mechanics for eigenfunctions and eigenvalues of two operators which are commuting, which are Lz and L square. And what we found is that these simultaneous eigenfunctions are so-called spherical harmonics, and eigenvalues are quantized. So they have values which are quantized with number m, which is what we call magnetic quantum number, and then with quantum number L, which we call a orbital quantum number. So L principal angular momentum quantum number and M magnetic quantum number. And so they take the values in these limits. So this quantization came from the fact that we required that our solutions were continuous, realistic, and so when we solve differential equations, linear differential equations, which correspond to this orbital momentum and operators, which we have introduced for describing them. So important part is obviously that these wave functions are normalized and they form a complete set. So therefore, other functions, which are functions of theta and phi in polar coordinate system, can be represented as a linear combination of spherical harmonics, which is a widely used property. So now we are now equipped to move to other systems which have also spherical symmetry or central symmetry. And so the first example of such system is a hydrogen atom. So hydrogen atom is a very important example of, or only example of electronic system which can be solved exactly because we have two particles, and for two particles we can solve quantum mechanical equations exactly. So when we come to say 2 electrons or 3 electrons or more, this becomes a so-called many electron system, and we will learn that actually we cannot solve Schrödinger equation exactly for them. So we now apply this fifth postulate, which we have introduced in our first section, to trying to solve equations for hydrogenic atoms. So hydrogenic means that we have still one electron, but the nucleus may have charge plus Z. So for example, we may have helium, but we have stripped it from one electron and we have helium plus, and this will be a hydrogenic atom. Or it could be uranium, but we have stripped, say, most of its electrons away and say left with one. So that may be a big number, but we deal with one electron, and so this system has a spherical symmetry, and electron is described by its interaction with nucleus, which is having this charge Z, and therefore described by this Coulomb potential. So our fifth postulate tells us that we need to introduce Hamiltonian. So Hamiltonian has kinetic energy and potential energy. And this is an operator which we now need to use. And the equation which we are now trying to solve is called Schrödinger equation. So in order to apply previous mathematics, so we need to go to a polar coordinate system. But actually, if we talk about hydrogen, so the masses of proton and electron are not that different. So therefore, we should have been using reduced mass for this system, this reduced mass mu. And so that introduces various corrections, as we'll see later. But what we do now, we just nail this nucleus. And so don't use reduced mass, but simply say, okay, so our nucleus is, say, completely stationary, and the electron is just moving in the potential of that nucleus. As we'll see later, this introduces some correction. And so in terms of numbers, the difference between, say, electron mass and effective mass of this system is different. As you can see, the difference is in the third and fourth decimal figures. So we have here 9, and here is, say, 104. So this is not a huge difference, but it makes some measurable difference in spectroscopic and other properties of hydrogen, which have been actually measured over the years very accurately now. And so you can see that we have quite accurate definition of masses, both electronic mass, but also effective mass of electron in hydrogen. So now we come to the Schrödinger equation. So still, since we nailed our nucleus, so we can solve this Schrödinger equation in spherical polar coordinate system as we did before. So we need to represent our kinetic energy and our potential energy in these spherical polar coordinates. And so now we have this r, theta, and phi. And you can see as we come to these spherical polar coordinates, we start seeing very similar terms in our Hamiltonian. So these terms, if we say try to separate them, so this term here looks very familiar, and so this corresponds to representation of L squared, as we saw before in our orbital momentum equations. So that means that actually we can rewrite this our equation in spherical polar coordinate system using, say, effective mass and also L squared operator, and basically separate the variables. So in the square brackets, we have terms which depend only on r, and so they are acting on the wave function, which is function of r, theta, and phi. And here we have terms like L square operator, which depends on theta and phi, also acting on this wave function. So this is part which is function of r only, and this part is function of theta and phi only. And so this is a sign that actually Hamiltonian, as people say, is separable. So that means that the eigenfunctions of this Hamiltonian are also separable, and so they can be represented by this product of wave function which depends only on r, on distance, and also the wave function which is represented by theta and phi. So we know the eigenvalues for, say, L squared operator, which is described by spherical harmonics. So these eigenvalues are h bar squared L plus 1. And so this allows us to simplify our equations for hydrogen atom and come to radial equation. So this radial equation, it has now, instead of L squared, by which we acted by operator L squared on the wave function, and so we have got its eigenvalue. So now we have h squared L plus 1, and the other terms are dependent only on r, as well as potential here. So now solving this equation, so this is quite a complex equation, and solving it is not very easy. So I'm not going to go in great detail from that solution. But let's start first of all, what are the simplest solutions which one can find, which are already very revealing and very important to remember their shape and say their kind of functional form. So if L is equal to 0, so obviously we have the simplest equation possible in this situation. And solution, this radial wave function, for hydrogen atom, in that case, has this very important form. So it's basically constant multiplied by exponent. And so this is a form which is kind of characteristic to all wave functions, which we are going to see later. So all of them have asymptotic behavior, or a behavior which is at long distances, which is exponential. So they are decaying exponentially away from the nucleus at long distances. So in this case, the exponent is ZR, and it is divided by this fundamental constant A0. And eigenvalues for this equation for, say, the lowest energy state, this eigenvalue can be also written in the form of combination of fundamental constants. So this is, say, charge of electrons and the electric permittivity of vacuum, and again, this famous A naught. So A naught is called Bohr radius, and so in some cases it kind of is viewed as a radius of the orbit of, say, ground state of electron in hydrogen atom. Of course, this is an oversimplification, but it gives the idea what is the size of a hydrogen atom. So this A naught determines what is the most probable distance at which you can find electron in hydrogen atom. So we'll come to that in a minute. So an important observation is that, say, if you go to higher values of L, total angular momentum creates a centrifugal force that pushes electrons away from nucleus. And so the sum of centrifugal potential and of the Coulomb potential gives rise to finite well potential. So it's not only simply Coulomb potential, but also we have a centrifugal potential. And so when we sum them up, so the potential of this electron in the atom is actually having this form here. And in this potential, we have these states, which are bound states of electron inside the atom. So this kind of general picture of what's going on if you take into account both Coulomb interaction and also the orbital motion of electron and the fact that actually it experiences a centrifugal force. Okay, so these are kind of qualitative views on what is going on. So the full derivation of the solution of Schrödinger equation for hydrogen atom you can find in many places. So actually, you'll see if you look, for example, at this website here, which is a very nice website and which goes in very great detail through how you go mathematically through this derivation, as well as lectures by Professor Grandinetti, and also there is a module from Edinburgh University. I attach all of them in the package which you get for this lecture as PDF files, so you can see how these derivations are made, basically using Laguerre polynomials and approach to solving different approaches to solving differential equations. So actually, interestingly, that as you will see, ways how these derivations are presented in all these three sources are a little bit different, which demonstrates a little bit different ways of solving, say, this differential equation. But still, this leads to the same and importantly precise solution of that equation. You can approach it also, I will mention here, from the point of view of variational principle. And so you can try to solve, say, find the eigenfunctions, saying values for hydrogen atom using also variational principle. Again, so I attach a PDF which describes that, which also provides yet another way of solving these equations. So I invite you to look at all of them in detail and see how, say, these equations are solved. As a result of that, you'll get, first of all, this very important fundamental value. So this comes directly, this combination of parameters, say, comes directly from solving this equation. And so this is this Bohr radius. Why it is so important? At the end of the day, it determines the size of everything on our planet, for example, because there is, say, in terms of, say, chemical interactions, so all atoms, say, talk to each other, and radii of atoms determine the size of molecules which get formed. So, for example, say this Bohr radius in hydrogen atom is about half an angstrom. But then if you put two atoms together, say you form hydrogen molecule, and it is already kind of an angstrom large, and then you put more hydrogen atoms, or you start putting them together with carbon atoms, nitrogen atoms, etc. And when you say put about 10 to 25 of these atoms together, you get yourself and your size. So this is a kind of smallest fundamental brick of size which we have in say our physical system on this planet. So this is why it is very important to remember also this number by heart. So it's 0.529, 10 to minus 10 meters, and use it later in many approximations which you can make. So now coming to a more general case, so general solution of the Schrödinger equation. First thing which we find is that, say, the general equation, the general solution for eigenvalues contains a quantum number. So this quantum number is what is called principal quantum number n squared. So it has been envisaged empirically or phenomenologically by Bohr when he analyzed the spectra of hydrogen atom, that actually he observed this quantization, and this is where this idea of quantization came from. Mathematically, it comes from solving this hydrogen equation, and again from boundary conditions. So if you look into these sources, which I recommended, and there are many others, you'll see how this quantum number appears actually from say, solving Laguerre polynomials and finding out the exact solution for equation. So you can see that the radial wave function also looks very complicated in the general case. So again, it has some constant, it has some polynomial attached to it, and it has this exponent. So this polynomial multiplied by exponent is a characteristic shape of this radial wave function. So important part is that on exponentially at long distances, it is again exponentially dying in all cases. But close to the nuclei, it has this complex Laguerre polynomial function. And so you can see that these Laguerre polynomials, they have a different number of nodes, and we'll come to that in the next lecture, for different numbers, for different principal quantum numbers and orbital momentum. So for example, in the simplest case, we have simply this Laguerre function equal to -1. But when we come to n equal 2 and l equals 0, we now find this term here. And then when we come to n equal 3 and l equals 0, we find even more complex polynomial, etc. So this polynomial multiplied by exponent and multiplied by r power l, this is a characteristic form of the wave function. And so later, because this is very complicated form, so it's very difficult to deal with it when we come to so-called basis sets, as you will see later. So this form has been simplified, and so there are some simplifications are very famous. So for example, Slater, so-called Slater wave functions, which say simplify them quite drastically. But then people abandoned this type of forms, exponential forms of wave function for orbitals, and turned to Gaussians and other types. Now, so if we look at n squared, so n is a quantum number which is also dependent on orbital momentum. And so we can, as also according to our postulate, so we always need to use normalization. So wave functions should be normalized, and so we find some constants for them. And so radial wave functions are normalized, and so therefore the total hydrogen atom wave functions are normalized too, because both components are normalized. So this is a kind of general overview of solution for Schrödinger equation for hydrogen atom. Again, just to recap, so basically we applied the fifth postulate, which tells us that actually, say, we need to use a Hamiltonian acting on the wave function and solve Schrödinger equation if we want to look at systems like that. And we constructed this Hamiltonian, we produced it in spherical polar coordinate system. We saw that it is separable. We found eigenfunctions for radial and angular components of the wave function and found these energies which depend on principal quantum number, as well as our wave functions depend on orbital quantum momentum, which has also these eigenvalues, as well as magnetic quantum number m. Fantastic. So then say the wave functions are normalized and orthogonal as they should be, and they have this form as we discussed. So these are say some polynomials multiplied by exponents, and now with angular momentum or with angular wave function, they also have this say cosine or more complex say angular components in these wave functions dependent on m and l values. And so obviously that is going to give us shapes of these wave functions, which we are going to talk about a little bit later. So, okay, so this theory, say the fact that actually Schrödinger equation can be solved exactly, and so it can, say, produce these quantum numbers and energies, could be used obviously to understand the hydrogen atom spectra very successfully. And so this was one of the first proofs of the strength of the quantum mechanics and the fact that Schrödinger equation actually can be used for it. And so these are famous spectra which have, say, this Paschen, Balmer, Lyman, and other series which correspond to transitions between these quantized states down to the ground state. And so this basically also supported the Bohr's model of hydrogen and other atoms. So these energies, say, you know, they are represented by the simple formula, which came out initially from, for example, for Balmer series, etc., when Bohr was working, I think, in Manchester in about 1913, and then have been derived from these equations. So this is how physics worked in this case. In terms of applications, for example, you may be interested to look into, say, hydrogen lamp, because this light, which is produced by hydrogen, can be excited by electrons, which can be accelerated between two electrodes, and they can produce this light. And so this is called a hydrogen lamp. So this is one of the curious applications of this theory. So what is of interest to us is that, first of all, we need to come to use or start using here Dirac's notations. So Dirac's notations have this bracket type of form. So we have quantum numbers here, NLM, and so we are starting to use them more and more in our discussion. And so here we come to some curious historic things, because it is customary to indicate the values of, say, 0, 1, 2, 3, 4 of the, say, this orbital momentum or azimuthal quantum number, L by letters S, P, G, F, G, etc. So these are kind of familiar notations for most of you, because here we start seeing S functions, P functions, so-called D functions, F functions, etc. So they come from this old-fashioned and outdated description of spectral lines, which I was just showing before. And so S stands for sharp, and then P for principal, and then D for diffuse, and F for fundamental. So this is a kind of very curious historical kind of thing where this SPDF actually come from. So these are spectra which people have been observing about 110 years ago, and which they called sharp, principal, diffuse, fundamental, etc. And then they explained them and called these different values of azimuthal quantum number as P, D, and F. So that is interesting. So basically this finishes kind of discussion about hydrogen atom. So the idea is that, say, using this explanation, you will have a very quick kind of overview of that. Then you will go into these sources which are recommended, go through the full derivation, look at this again, and then we will come to analysis of how these wave functions, which we have been discussing, look like at their shapes. Again, say these familiar, say spherical and dumbbell, etc. shapes. Where do they come from the point of view of this hydrogen atom solution? So this will be in the next installment of these lectures. So